Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about intermolecular forces, or in your book as described as attractions. And there's three main types of intermolecular forces. We have what we call as dispersion forces, dipole interactions, and hydrogen bonding. Okay, these are the three main types of attractive forces, and I'm going to go through each of these. Okay, the first two, dispersion and dipole interactions, are also called van der Waals forces. Okay, I will not use this term very often in class, but please be familiar with this term. If it's saying van der Waals, oh, we're thinking of intermolecular forces, specifically dispersion and dipole interactions, and I'm going to go into both of those. Okay. So dispersion forces are the weakest of the three, okay, and they're also called London dispersion forces. I'll rarely use this term, but if you're watching a video and someone says London dispersion, you can just refer it to as dispersion forces, okay? And they are caused by the motion of electrons. So what we know is that hydrogen is going to form a single bond with another hydrogen. And we know that hydrogen is now satisfied with its octet. Okay, it's now has a full octet, and it's not going to be wanting to react with anything the way it's sitting right now. Okay, because it's stable, but the motion of electrons around hydrogen sometimes shift to one side or the other, and when it does that, it creates this temporary dipole that's happened, and we now have a partially positive and negative side. You see how there's kind of a buildup on this side of this molecule, and it's because they are dispersing to one side, and they are a little more heavy, negative on one end, so now it's going to be wanting to be attracted to others. And if we have another one that also has electrons moving, you see how there's kind of like a bulging side here? These positives will want to be attracted to the negative side, so they'll be temporarily attracted, just kind of weakly, and then when those electrons move around again, they will just go back to being stable and non-attractive. So it's just a temporary force, and it's just this weak attraction that occurs when those electrons are just moving around. Okay, so this force is essentially just the movement of electrons, and it's uneven for just a moment, and it creates this temporary dipole that allows for them to stick together. Okay, and if you can't remember what a dipole is, I'll just draw it right here. Okay, a dipole looks like this. Drew it a little long, okay, but it's the positive end pointing to the negative end of this spectrum here, okay, of these engineering electrons. They're not complete charges, they're just partial. Okay, it's not an ionic bond like we've learned in the last chapter, but it's a positive pointing toward the negative end of it, so it acts like a magnet. So if you see one of these dipoles, you can just assume it acts like a magnet. Okay, the second of the three is dipole interactions, and this is kind of our intermediate force. Okay, dispersions are the weakest, dipoles are the second, I guess in the middle, weakest, almost strongest, and then we have hydrogen bonding, which is our strongest. But dipole interactions are when we have a permanent dipole. Okay, so if we have iodine and chlorine bonded to each other, okay, they're forming a covalent bond, but chlorine's a little more electronegative than iodine is, so it's going to steal those electrons, and it's going to want to have those electrons on one end, and it's going to be sharing them unevenly. And then there'll be an iodine over here bonded with a chlorine, and this iodine is going to be losing its electrons to chlorine, and it's going to form a bond. And we call that a dipole interaction, okay, because there is a dipole that's happening here. And if we look at this image down below, okay, this is just showing a network of them. So if we have a positive and negative end to this compound, what's going to happen is it's going to have other ones that are like magnets, and they're going to arrange themselves so that they are attracted to the proper end of the atom. Okay, because these chlorines are going to be attracted to these iodines, and this iodine is going to be attracted to this, these chlorines are going to be attracted to the iodines. Okay, and these have permanent dipoles, so they look like this. Okay, so they're all going to be pointing at each other, okay, based on their charges. All right. And then the last type is a special type of dipole interaction, and it's called hydrogen bonding. Okay, it's basically the same thing as dipole interactions, except that it's going to be a lot stronger, and it's specifically to water. It's a specific thing to water, and it does occur in other atoms, but water is the most common example. Okay, because we can see that this oxygen is combined with two hydrogens, and it's got a negative and positive end, and it's going to be very polar. Okay? And there's actually a dipole that runs right through the middle of this atom, like this. All right, it's got the positive end pointing toward the negative end, and then down below we have a network of these molecules of water, and they're going to arrange themselves so that their charges match up with the opposite charge. Okay, and the reason we call it hydrogen bonding is because hydrogen is now bonding with the negative end of the other water molecules. And remember, there are lone pairs floating around on the outsides of these atoms, of these molecules. Okay, so remember, now it's even more negative. This is a very negative end, and these hydrogens are going to be attracted to the other very negative ends of this water molecule. Okay, so this is just a special kind of hydrogen bonding. And then down below, we can see that methane, okay, these are CH4 atoms, and they're not combining. There is no forces happening in between them. I put an X there. It's not a plus, but I wrote it. I'm looking at it kind of sideways. All right, and there is no bonding happening, even though there's hydrogens here. Well, why is that? Well, it's because methane is not polar. It does not have a dipole. There is no dipole present in this molecule, but in water there is. In iodine monochloride, there is a dipole that exists. Okay, all right. So if it basically likes want to be with likes, if these act like little magnets, they're going to want to stick together. If this is not like a magnet, it's not going to want to stick to really anything. If you think of like a plastic marker or pens, like they're not going to want to stick together. They're just going to kind of fall apart. And that's why methane is a gas, because they're not interacting with each other. But water at room temperature is a liquid because they're wanting to interact with each other. Okay? We're now thinking beyond just the bonds inside of a molecule, but in between these different molecules, what is going on in between? And this gives us all kinds of macroscopic properties. All right? And including that is volatility. Okay? This will not be heavily on your test or anything, but I put it in the online textbook because it just helps build this concept of why is it that certain compounds are liquids or gases at room temperature. Okay, so if we look here, bromine is highly volatile. Okay, and what does volatility mean? Okay, it's a measure of how easily a liquid evaporates. Okay, if we look down here, bromine can easily evaporate and turn into a gas. It's basically kind of in this quasi-liquid gas state at room temperature. Okay, and it's because bromine has dispersion forces, and they are the weakest of the three forces, and they're going to be just every so often be attracted to each other, and then they're going to separate, and then they'll be attracted to each other and separate. It's because the electrons are just moving around. But when we compare that to ethanol, ethanol has a hydrogen bond forming, okay? Has this alcohol group on the end of this compound. And what we're seeing here is that there's this bonding that's happening, and it's permanent. It's going to be a strong bond. You see how these dots are really small, and these dots are a lot heavier? So they're going to be attracted to each other. If they're going to be attracted to each other, then that means they're going to want to stick together, and they'll probably be in a liquid phase. To turn this into a gas, we need to give it some energy. We need to apply some heat to the bottom of this round bottom flask, and it will cause those atoms to vibrate faster and faster, and eventually they'll break free. Just like water does. Water at room temperature is a liquid, and if we add heat, those molecules those hydrogen bonds start to break, and all of a sudden now you have a gas forming because they're now spreading out and they're moving quickly. They're gained energy. All right, so the state of matter that something is in is based on these three forces, okay? And also, this gets into kind of like our melting points and boiling points. I just kind of want to point out a small section here, focusing on halogens. So in this example, it's talking about chlorine, bromine, and iodine. And if you look up on my poster in my class, they're colored. Chlorine is a gas, bromine is a liquid, and iodine is a solid. Okay, but they all share characteristics because they're in group 7. But why is this one a gas, is this one a liquid, and why is this one a solid at room temperature? And that's because as the dispersion forces, the weakest of the 3 kinds, okay, how they're unevenly sharing electrons, okay, because all of these form these diatomic molecules, like chlorine, bromine, and iodine all form these pairs, okay? And chlorine is a much smaller atom, and there's less electrons moving around. So with it being less electrons moving around, they don't tend to build up on one side as easily and create that attractive force. But iodine has 106 electrons, okay? And its dispersion forces are the strongest in iodine because there's more electrons moving around, and it creates a more opportunity for those dispersion forces to attract to each other and to be bond and to make those connections. While chlorine has the smallest number, and there's less opportunity for those dispersion forces to occur. Okay, so this concept here is more of just an addition. It's not going to be on your test or anything. This is just kind of above, but I want to talk about it just because it builds on what we're talking about and how we relate it to the macroscopic world. Okay, thanks again for watching, and until next time, we'll get into these other concepts in chapter 4. Okay, this will be it for chapter 3. Okay, thanks again for watching. Bye.